Hello everybody. In our series of lectures on basic electronics, learning by doing, let us move on to the next one. Before we do that, let us recapitulate what we discussed in the previous lectures, couple of lectures. You might recall that we discussed about the various characteristics of operational amplifiers. You can see on the screen I have listed them: input offset voltage, input bias current, output resistance, input resistance, common mode rejection ratio or CMRR as it is known, transfer characteristics, the gain bandwidth product and slew rate, etc. We also showed how these parameters can be measured in the laboratory. So now let us move on to certain applications of operational amplifier. So I would like to take some simple application circuits of operational amplifier. The first example I would like to take is an inverter non-inverter circuit. So a circuit which will be both inverter as well as a non-inverter by just modifying certain things. So that is a circuit I want to discuss now. You can see the circuit is shown on the screen now. This is a very simple circuit, maybe which is very familiar to you because we have seen several similar circuits earlier. You can see there is an R and R, the feedback resistor and the Ri both are R here, equal resistors, and the op amp you get the input voltage signal is applied simultaneously to both to the non-inverting input as well as the inverting input. So if I have a circuit like this and if I give a V in signal here, what will be the output? So you may perhaps feel momentarily that it is somewhat tricky because the input is driving both the inputs, and therefore what will be the net output, the effective output. But I can assure you it is not going to be very difficult to understand because we have already learned some of the theorems which will help us in understanding even complicated circuits. You might remember we discussed about the superposition theorem. I am sure many of you would immediately recognize that using superposition theorem we can understand the working of this circuit. So what is that we have to do? It is very simple. If you see on the screen, if I now assume the V in is driving both the inverting as well as the non-inverting input. So if I now ground this non-inverting input and apply the voltage only to the inverting input, then it becomes a very simple exercise because it is a inverting amplifier and the feedback resistor is R, the input resistor is also R, therefore the gain is minus R by R, that means minus 1. So it is a very simple inversion circuit. It is inverting whatever is the amplitude at the input correspondingly at the output. It just provides 180-degree phase shift between the input and output. So when I ground the non-inverting input, the amplifier becomes a very simple inverting amplifier. Okay, that is first part of the superposition theorem. Now what we will do, if the second part I have to ground the inverting input and apply the signal only to the non-inverting input, that is the next option. When you do that, you would find the circuit becomes totally a non-inverting amplifier. So I have shown here, for example, the total voltage gain that I get, AV is the total voltage gain of that circuit, will be by superposition the gain of the amplifier when it is only an inverting amplifier, that means the non-inverting input is grounded, plus the gain of the amplifier when it is acting only as a non-inverting input with the inverting input connected to ground. So AV, the total voltage gain, is equal to A inverting plus A non-inverting. That is what we want to look at. That is what I was just mentioning to you by using superposition theorem. So now let us see in more mathematical terms how it is. So you can see that 3 is grounded, this is the first part, we applied input is only at the inverting input, and the gain is R by R, therefore it is 1, but because it is inverting you have a negative sign, minus R by R times V in is the output voltage, VO1 I call it, because it is a first configuration, and therefore it becomes minus V in, or if I want to look at as the gain, VO1 by V in is equal to minus 1. You can all see this, very simple. Now I go to the second configuration in the superposition, where I ground the inverting signal input and apply the input only to the non-inverting. Then what happens? It becomes a very simple non-inverting amplifier, and for a non-inverting amplifier we have seen several times output voltage, now I call that VO2. VO2 is equal to V in, the applied voltage, multiplied by a factor which is 1 plus R by R, 1 plus R2 by R1, where R2 is a feedback resistor. Here because the two resistors are equal, R and R, it is 1 plus R by R, and that means it is 2. So VO2 is equal to 2 times V in, or the gain of the non-inverting amplifier is 2. So I have found the gain of the inverting amplifier separately and the non-inverting amplifier separately. Now all that I have to do is I have to add them together to get the total voltage gain of that amplifier. So V output is therefore is equal to VO1 plus VO2, where VON due to non-inverting, VO2 due to VO1 is due to inverting, and VO2 is due to non-inverting. So this is minus V in, as we have seen already, and this is 2 V in, and therefore what I left with is V in. So V output is equal to V input. That means it is a non-inverting amplifier effectively, and the gain is 1. VO by V in is the gain, and that is equal to 1. Therefore when I have simple configuration like the one I showed you at the beginning, and if I have this circuit with the two resistors equal and apply the input voltage here, I will exactly get the same voltage at the output. But if I disconnect this and connect it to ground, it becomes an inverter, and therefore the gain becomes minus 1. Therefore you can see this circuit can easily be used to switch between inversion and non-inversion. That is what I want to show you as the next application. After learning by using the superposition theorem the earlier circuit, you can immediately recognize that I can now have an amplifier which can switch between inverting amplifier to a non-inverting amplifier. So if I want inverting amplifier, it is very simple. So for example, I have replaced one of the wire that you saw in the previous circuit with a switch here. It is called single pole double throw key. Therefore you can have either connect this terminal 3 to ground, or you can connect it to the input V in. When I connect it to ground, you can immediately see it becomes a very simple inverting amplifier, because you are giving the R are equal and you are giving the input at the inverting in terminal, and therefore the gain will be minus R by R times, and that means minus 1. So it is a simple inverting circuit when I put the switch to the ground with reference to the non-inverting terminal connected to the ground. But when I want the other configuration, that is what I have shown here, AV for this configuration is minus R by R times that is equal to minus 1 time, because R is equal to R. If you want a gain, you can always put the feedback resistor 2R, 4R, 10R, whatever, and correspondingly you will get the gain. But here we just want an inverting or a non-inverting amplifier selectable by a simple switch. Therefore we have kept the resistors equal to, so that we do not get any gain, we just get an inversion or a non-inversion, right. So this is the first part where it becomes a simple inverting amplifier. The two resistors are equal and you are only operating the non-inverting the inverting mode, and the non-inverting terminal is connected to ground. Therefore the gain is minus 1. I hope you get the point. Now what I do, you can see I have switched the non-inverting input to the input voltage rather than to the ground. So previously it was here, now I have shifted it to the input. In this configuration it is the same as the circuit which just now we discussed by using superposition theorem in 2 stages, and therefore you know what is the gain of this circuit. The gain of this circuit is plus 1. You might remember that by superposition theorem the gain of the non-inverting amplifier is 2, the gain of the inverting amplifier is minus 1. So when I add them together, 2 minus 1 gives me 1, therefore it becomes a simple amplifier with a gain of 1. Therefore it is a non-inverter. Whatever input I give V in, I get at the output. So by selectively choosing the 2 terminals corresponding to the non-inverting terminal of the op amp, whether I connect it to ground or to the input voltage, you find I can switch the amplifier to be a inverting amplifier or a non-inverting amplifier all with a gain of 1. Right, that is exactly what I have shown on the screen. A non-inverting is R by R plus 1, that is equal to 2, and therefore for that algebraic sum is AV is equal to A inverting plus A non-inverting, that is equal to minus 1 plus 2 is equal to 1. Therefore the circuit is a switchable inverter non-inverter circuit, and it has got a gain either 1 or minus 1 depending upon the position of the switch. So it will be sometimes very useful in different applications, and therefore I wanted to discuss this. Now what I would do is I will quickly show you the same circuit wired on the breadboard, and I will show you how this can be very easily switched. Instead of using a switch, I will use the same wire, one single wire which is connected to that inverting non-inverting terminal. I will either connect it to ground or to the input of the inverting terminal. Thereby I will show you what happens to the gain at the output. I want you to see the circuit here. It is the same as the one which I showed you just a couple of minutes ago. So you can see there is a operational amplifier 741 at the center. There are 2 resistors which are called R and R in our circuit. This is 10 kilo ohms, this is also 10 kilo ohm, and you see here that non-inverting input can be either connected to the ground or connected to the V in input by using this switch. Instead of the switch, I am going to use a wire which can be connected either to this end or this end. That is the only difference. The same circuit is wired here. I am sure you can see the operational amplifier there at the center, and this is a power supply, this is the plus 12 volts line, and similarly at the bottom you have the minus 12 volts. With green wire shows the minus 12 volts, and the black wire corresponds to the ground connected to the dual supply that I have at the back. Now it is actually connected to the ground. This input is exactly in the same way as it is shown in the circuit. It is connected to the ground, this yellow wire, and for the input I am using a millivolt source, which is also very familiar to you. We have used this in the earlier experiments also. This is a millivolt source, and the output of the millivolt source is connected as the input, and the output of the operational amplifier is connected to a multimeter which is in the voltage scale, and it is now reading minus 1.01, which is the output voltage. So the output voltage now for this circuit is minus 1.01. Now what I want you to see is, let me quickly take out the multimeter from the output and connect it to the input, and at that time you observe what the multimeter reading is. Now I have just removed the multimeter from the output pin number 6 and connected to pin number 2 to the inverting this end. I have connected the multimeter here. So what it is now measuring is the input voltage from the voltage source, and I want you to observe the multimeter. You can see it is showing plus 1.01. So the input voltage is plus 1.01 and the output voltage we measured minus 1.02. Therefore there is only a simple inversion. I give 1 volt here, I get minus 1 volt at the output. I will again quickly take it out and connect it to the output once again. So now I have connected to the pin number 6 again the same multimeter, and I want you to observe the multimeter. It shows minus 1.01. Therefore there is a just inversion, nothing else. Therefore it acts as a inverter because I have connected the inverting non-inverting terminal to the ground. What I am now going to do is remove that wire and connect it to the input. It is equivalent to having a switch and switching it off on the other side, pushing it onto the other side. So I am going to take out this yellow wire and connect it to the input, and let us now see again what is the input and what is the output. I have now switched the yellow wire from ground to the input terminal, and I am now monitoring the input voltage using the same multimeter. I want you to see the multimeter. When you look at the multimeter, you find multimeter shows 1.02 volts, that is the input voltage, positive voltage, because I have connected the multimeter now at the input. Quickly I am going to take out here and connect it to the output terminal, and again I will ask you to look at the multimeter output. Now I have switched the multimeter to pin number 6 as usual, and now multimeter will be measuring the output voltage, and output voltage is also 1.02 plus. That means there is no inversion, and the same voltage which is given at the input is measured at the output. Therefore it acts as a non-inverting amplifier with a gain 1. Previously it acted as a inverting amplifier with a gain -1. Therefore I am able to switch the amplifier to non-inverting or inverting by just switching this wire between the ground and the input. That is all I wanted to show you. So we have seen the very simple demonstration of the switchable inverter and non-inverter circuit. Now you can immediately imagine that the same thing can also be done using some device. So the next one I wanted to discuss is a JFET controlled switchable inverter. JFET means what? Junction field effect transistor. Junction field effect transistor controlled switchable inverter is what I wanted to show you, and the input signal drives again both the inputs of the op amp simultaneously, the inverting as well as the non-inverting, and therefore we will get an amplification corresponding to the inverting amplifier as well as a non-inverting amplifier, and the effective output will be the superposition of these two. So we will get a very interesting result here also. So you can see in the circuit which is shown on the screen, you find this symbol. I am sure you are able to recognize this is the junction field effect transistor, and I give a pulse here. So the pulse is from 0 to 6 volts. When it goes from 0 to 6 volts, when it is positive, this FET will be conducting, and when it is ground, it will be not conducting. So you can see that. Now the JFET acts like a voltage controlled resistance in principle. Depending upon the voltage you apply at the gate, the resistance between the drain and the source can be very low or very high. Now what is going to happen when the gate voltage is low? That means I have 0 volts at the gate. That means the output voltage JFET will become open. The resistance of the JFET when there is no gate voltage will be very high. It is almost like open, so like an open switch. Therefore the input signal, when that happens, that means this is open here, this terminal, and that means the input voltage is driving both the inverting and the non-inverting input simultaneously, and the values of resistors are the same. If that is the case, you know what is the total voltage gain. We have seen it earlier also by using superposition, and the total voltage gain is 1. We have already seen that. So when the gate voltage of the JFET is 0, you get a very simple non-inverting amplifier with a closed loop gain of 1. When I have, similarly when I have the high for the thing, then this will become on. When this becomes on, the JFET offers very low resistance at this end, and that means it is almost connected to the ground. When this is connected to the ground, that non-inverting input is connected to the ground. When that happens, only the inverting input is driving the amplifier, and therefore the gain will be minus R by R, that is -1. So by using this square pulse, I can switch back and forth as an inverting or a non-inverting amplifier. The same thing I showed as a demo, except that I was manually switching. I am taking the wire, I am connecting to the ground now, I am now connecting the wire, the same wire, to the input terminal. That is what I did. The same thing can also be done electronically by switching it electronically by making use of an FET as a switch here. When I apply a low voltage on the gate, the FET is open. When I apply a high voltage on the gate, the FET is on like a switch, and therefore I can switch by sending a square pulse on or off, and thereby I can convert the amplifier as an inverting or a non-inverting amplifier. That is, so this you can also electronically select whether you want +1 or -1 as the gain. That is the advantage of this circuit. Now there is also another variation of the circuit similar to what we have already seen, that is an inverter with adjustable gain. You can change the gain of the inverter from some low value to a very high value, whatever value you want. So I am showing another application circuit of the operational amplifier, which is an inverter with an adjustable gain. What you have here is a very simple circuit which you can very easily recognize. I have R2 by R2 and R1 as the feedback and the input resistance for the inverting in terminal, and for the non-inverting terminal again I have a potential divider. I have an R2 plus an R2 which is a variable, that means it is 0 to R2 variable resistor, and that is connected to the ground. So what will be, how do I analyze the circuit? I understand what will be the gain of the circuit for different variations of the value of R2 here at the non-inverting terminal from 0 to the value maximum value R2. If I vary, how will the gain change? That is what we are interested in. For that, what I will do is, if I assume that the variable resistor is 0, that means the potentiometer I keep in 0 value. If I do that, it is equivalent to saying this terminal is connected to ground. When this terminal is connected to ground, the non-inverting input, the circuit becomes a simple inverting amplifier, and the gain of the inverting amplifier we all know by now, it is minus R2 by R1. So that is what we have shown here. So the maximum gain that you can get is minus R2 by R1 when this potentiometer is having a value 0 resistance. But when I make this resistance maximum, that is corresponding to R2, then what will be the gain? That is the next question that we have to ask. When this resistance becomes R2, you find V in is applied between the ground and V in. You have two resistors connected in series, both of them are equal. Assuming the input resistance of the operational amplifier to be very, very large compared to these resistors, you find what is going to happen is these two resistors going to divide, potential divider circuit. It is going to divide the V in, so that the V prime, which is the actual voltage at the non-inverting terminal, will be V in by 2, because the two resistors are equal. They will divide into half, and therefore V prime will be V in by 2. So the effect of having these two resistors is, when I have R2 full value, the potentiometer, I will only apply half of the input voltage at the non-inverting terminal. So when that happens, what is the voltage gain? The voltage gain for the non-inverting amplifier is 1 plus R2 by R1 times V input. The V input here is not the actual V input that we have applied, but V prime, which is the effective voltage after the potential divider applied at the non-inverting terminal. And V prime we have already seen is V in by 2. So if I substitute that and simplify this expression for a superposition, that this is the gain corresponding to the non-inverting, and then there is also inverting terminal always present, therefore that will give minus R2 by R1 times V in. So the total gain of the amplifier, or the thing will be, when you simplify this, you find this becomes V in by 2 into 1 minus R2 by R1, and if I make R2 by R1 equal to 1, then V in by 2, 1 minus 1, that is equal to 0. Therefore the minimum gain is 0, and whatever is the maximum gain you can get minus R2 by R1 when you have only the inverting amplifier. Therefore you can vary the gain of this amplifier from minus R2 by R1 to 0. So the total voltage gain of this amplifier can be varied over a range by using this type of a configuration. So this is maybe another useful circuit. I will show you the circuit also, demonstration of this circuit also Now, I want you to observe the circuit here. It is the same as the one I showed you just a few minutes ago. You have an operational amplifier 741 and you have a 1K resistor here. Here also 1K, this is 1.0K, this is also 1K. So, both are equal, and I have a 1K resistor here, and also I have a variable resistor potentiometer here. And so, when I vary the potentiometer from 0 to a maximum value, the gain should go from minus R2 by R1, in this case it is 1, minus 1 to some different values. I can vary by varying this potentiometer. That is what I wanted to show you. You can vary the gain by changing this potentiometer. So, here the input is again from a voltage source, and the output, I have not changed the output, it is again about nearly 1 volt. So, that is connected at the input of the circuit, and now I am measuring the output of the circuit by from the 6 I have connected the multimeter, and if you observe the multimeter, it shows 0.85 with the potentiometer in 0 position. You can see the potentiometer I have got here connected, the potentiometer is here. So, the potentiometer, you can see I have taken only the one end and the middle, and that is what I have connected in the circuit. Therefore, when I put it at the extreme end, and it is now at the extreme end, you find it is 0 resistance. When it is 0 resistance, now if you observe the multimeter, it shows 0.85 volts, minus 0.85 volts. I hope you are able to see that. Now, that is the output voltage. Let us see what is the input voltage. I will quickly vary the multimeter connection and connect it at the input. Now, if you look at the multimeter, you find it is plus 0.84. So, the input voltage is 0.84 volts, and the output voltage you observe was minus 0.85 volts. Therefore, the gain is minus 1. The gain is minus 1 in this configuration when the potentiometer is maintained at 0 position, corresponding to this connection going to the other end. Therefore, non-inverting input is connected to ground when this is 0. Now, when I increase the resistance, see what happens. I would like you to observe the multimeter after I connect it to the output terminal. Now, you please observe as I move the potentiometer what happens to the output voltage. You can see it is decreasing. It is now 0.85, it has come to 0.33, and I can keep on going till I get 0, which will be corresponding to my potentiometer corresponding to 1K. So, you find the output voltage can be varied by varying this potentiometer, and that means I can vary the gain of the amplifier by using this potentiometer from a minimum 0 to a value of minus R2 by R1. It is on the inversion side. Therefore, minus R2 by R1 will be the gain. In this case, both are equal. Therefore, I get a gain of 1. So, this is a very simple circuit corresponding to a inverting amplifier with a variable gain, with an adjustable gain. So, we saw how an adjustable inverter can be gain of inverter with a gain which is adjustable using a potentiometer can be constructed in a very simple scheme by using the operational amplifier. Now, let me move on to the next application circuit, which is a sign changer. You have already seen something very similar to this. When you get a inverter non-inverter plus 1 to minus 1, that is again a sign changer, as you can see if I get a gain of 1. But there is a slight variation between this circuit which I am going to now discuss and the earlier circuit which I have discussed. What I have done here is I have now replaced the R1 R2 that you saw in the previous example. I used 2 resistors. If you remember, now I ask you to look at the screen. I had one resistor here R2, and I had another potentiometer here which can go from 0 to a maximum value of R2. Instead, what I have done here in this circuit is I have just used one single potentiometer. Therefore, the wiper can be connected to the non-inverting input, and therefore, this wiper can be at this end. When that happens, I get the full resistor here connected to ground, and the input is connected to V in, and when I take the wiper to the other end, this end, it is connected to ground. That means the non-inverting amplifier is connected to ground, therefore, it becomes an inverting amplifier. So, when I have a very simple potentiometer without having a switch, you can see I can vary continuously the gain from -1 to +1. I am sure you can immediately recognize it is a modification of the switchable gain. In the switchable gain I had only two gains, either it is +1 or it is -1. There is no other value in between, whereas here I can go from -1 to +1 by modifying, you are very simply replacing the switch by a potentiometer and making use of all the three terminals of the potentiometer. One end I connect to the input, the other end I connect it to ground, and the variable end I connect it to the non-inverting terminal of the operational amplifier. When I do that, you can see I will be able to vary the gain from -1 to +1 continuously by changing the position of the potentiometer, varying the value of the variable resistor. Okay. So let me just try to understand the operation. When the wiper is all the way to the right, that means it is at the end, right end here, that means you have the non-inverting terminal connected to the ground. So the non-inverting input is grounded and the circuit has a voltage gain of AV is equal to -1. We all know that it becomes a very simple inverting amplifier. But when the wiper is all the way to the left, the input signal drives both the inverting and the non-inverting input. In that case, the total voltage gain is a superposition of the inverting and non-inverting voltage gains. So let us try to look at, we have already seen that earlier in the beginning also. So the non-inverting gain is 2, the inverting gain is -1, therefore total gain is 1. So these are all known. What is the only difference? I am not just switching, but I am using a potentiometer and going from the ground to some value, and therefore the gain is going to vary from -1 to +1. That is all, the very simple thing. So as the wiper is moved from right to the left, the voltage gain changes continuously from -1 to +1. At the crossover point, when it is exactly at the center approximately, a common mode signal drives the op amp and the output should ideally be 0, but you would find it can have some small millivolts which are due to the offsets of the current and voltage. So now I will show you a demonstration of the sign changer, and later on we will take one more example of an application circuit. So the sign changer, what I am going to do is just replace the two resistors that I had previously and use only one single potentiometer, and then show you that the gain can be varied from -1 to +1 continuously. Now you can observe the same circuit I have drawn here. You have the operational amplifier, you have the two resistors, both are 1K and 1K, and you have a potentiometer here with the three terminal, one terminal connected to the ground, the other terminal connected to the input, and the third terminal, which is a wiper, connected to the non-inverting input. So this is the same circuit which I just now discussed, and the same thing is wired here. So you can see the op amp and the various connections made there, and you can see the potentiometer here with the three wires, the green, the black and the yellow. The yellow is connected to the ground, the black is connected to pin number 3, and the green is connected to the input. So that is the way, and the input is from the voltage source which you have already seen, and I have not disturbed the voltage, and that means it is still 1 volt. From the beginning, for all the demonstrations I have used this voltage source to be the same 1 volt, and so it is now the same 1 volt. And now I want you to observe, I have connected the multimeter at the output of this amplifier. At this point I have connected the multimeter, and I want you to look at the multimeter output. If you see the multimeter output, you see it is 1 volt. That means when the potentiometer is in the maximum position, then you find the corresponding gain is 1, and so when I give 1 volt I also get output 1 volt. When I change the potentiometer, this should go from +1 to -1 continuously. That is what I wanted to. Please observe only the multimeter. I am going to now vary the potentiometer and see what happens to the gain. I am varying, but I want you to observe only the multimeter. Please observe the multimeter. You see the gain now starts coming down. As I increase the potentiometer, the gain keeps coming down, the output voltage keeps coming down, and then almost I come to 0, and then you see as I keep increasing, the gain starts increasing the negative side, -374 5, 6, 7, etc. When I go to the maximum, you find it has come again to nearly 1 volt minus 0.91, which is equal to closely minus 1 volt. Therefore, I have changed from plus 1 to minus 1 continuously the gain by changing the potentiometer from a 0 value to a maximum value. So, this is what we call a sign changer. You can change the sign of the amplifier by continuously varying this from minus 1 to plus 1 or plus 1 to minus 1 by using the potentiometer. So, this is again a very simple and useful circuit for applications. Now, we have seen different circuits. One is just switchable from minus 1 to plus 1 by changing one wire or a switch. You can change the gain of the amplifier from minus 1 to plus 1. Then we also saw another circuit where you can vary the gain from some low value, for example 0 to some minus R2 by R1, where it could be R2 by R1 can be 1 or 10 or whatever number depending upon the ratio R2 by R1. So, we also saw how you can have a variable gain amplifier, and the third circuit we saw how you can go from minus 1 to plus 1 continuously by using a potentiometer. Now, we also wanted to show you another variation of the circuit where you can go from minus n to plus n, where n is some number, maybe 10, 8, 5, 20, whatever. So, is it possible to design a circuit which will provide me with a continuous variation of the gain from a minus n value to a plus n value. So, that is what. So, this is called adjustable and reversible gain. The gain is adjustable as well as reversible. You can go from plus to minus as well as from some 0 to a large value, both are possible. So, the one such circuit is shown on the screen. As you can see, what I have done here is I have generalized the circuit. I have put a R here at the input and I have put a NR, N times R, and that is a feedback resistor. And at the inverting input, you can see I have used another resistor whose value is N by N minus 1 times R. The product here is N by N minus 1, or the value is NR by N minus 1. I also have a variable potentiometer as I had in the previous case here. So, now let us try to understand how this circuit works, and what it is going to do is it is going to give us adjustable voltage gain from minus n to n. It is similar to the type of the amplifier that we saw, which we called sign changer. The sign changes from minus 1 to plus 1 continuously by using a potentiometer. A very similar circuit is seen here. Also we are using the potentiometer in a very similar fashion, but apart from that we also have got the feedback resistor n times more, R and NR. So, now let us look at the circuit when the wiper is at the bottom end, the right end. When the wiper is at the end, at this end, you can see the non-inverting input is connected to the ground, and therefore the input is only applied at the inverting terminal, and the feedback resistor is NR. Therefore, the gain is minus NR by R, and that is minus n. We have already seen, except that in the earlier case we have not used NR, we just used R. Therefore, the gain was minus 1. Here I have used NR, therefore the gain is minus n. That is all the difference. So, the gain of this amplifier is minus n, minus NR by R, and therefore minus n. When the wiper is at the lower end corresponding to the ground. What happens when the wiper is at the other end, maximum end, when the value of the resistor, variable resistor, is included in the circuit corresponding to the non-inverting terminal? When this happens, what will be the effective gain? To find the effective gain by superposition, now you can see, if I assume it to be a non-inverting amplifier, you find the Vin is connected to the non-inverting amplifier by superposition. At that time I should ground this terminal and then calculate what is the gain. After that I should ground the non-inverting terminal and assume only these resistors are present and the input is driving only the inverting terminal, and find out what is the gain, and I should add the 2 to get by superposition theorem to get the overall gain of the amplifier. So, before I do that, what I have done is, if I ground this terminal, then I have 2 resistors connected to the ground in parallel at the inverting input. Then what will be the effective resistance of these 2 resistors? So, I have connected, I call them R prime, and I have calculated that NR by n minus 1 multiplied by R divided by NR by n minus 1 plus R, R1 into R2 divided by R1 plus R2 is the effective resistance of 2 resistors R1 and R2 connected in parallel. We have already discussed that very long back in our earlier parts of the discussion, and therefore NR by n minus 1 into R divided by NR by n minus 1 plus R is the effective resistance of these 2, and that when I simplify becomes NR by 2n minus 1. Now, when I have the non-inverting amplifier, the gain will be 1 plus R2 by R1. 1 plus R2 is NR, R1 is this effective resistance, because both the resistors will come in parallel connected to ground, and therefore I have used that value NR by 2n minus 1 as the denominator. Therefore, NR is in the denominator, 2n minus 1 comes into the numerator, and therefore the value of the non-inverting amplifier becomes 1 plus NR by NR into 2n minus 1, that is nothing but 1 plus 2n minus 1, therefore 2n. So, A non-inverting input is 2n, and A inverting we have already seen is minus n. So, when I connect both of them together, the total value will be A non-inverting plus A inverting, 2n plus minus n, therefore it is n. So, you see, when I have the wiper to the ground, it is only an inverting amplifier with a gain minus n. When I have the wiper to the left extreme point, then you find I have a gain of n. So, when I change the potentiometer from the minimum value 0 value to a maximum value, the output gain should vary from minus n to plus n. So, therefore, this is a adjustable gain amplifier, where the gain could be chosen by choosing the value of the resistors NR and R. I will show you the circuit and tell you. I am going to demonstrate this circuit now, where I will show you the various things. What I have done is, I have chosen n to be 10, for example, for simplicity. Therefore, R is going to be 1k, NR is going to be 10k. If this is the case, then what will be the NR by n minus 1? N is 10, therefore 10 by 10 minus 1 is 10 by 9 times R. So, 10 by 9 is almost equal to 1, therefore I will make this also equal to 1k. So, I have 1k here, I will have 1k here, and I will have 10k here, and I have a potentiometer, it could be 1k or 5k, it does not matter. When I put it on this extreme end, I will get a gain of minus 10, because NR by n minus n, and when I put the potentiometer to the left extreme on the screen, then the gain will be plus n, that is plus 10. So, I should have a gain of minus n to plus n as I vary the potentiometer in the circuit. This is what I want to demonstrate to you now. Now, you can see the circuit here, it is the same as what I have shown you earlier. So, I have NR is 10k, the R is 1k, therefore, n is 10. This is 10k resistor, this is 1k resistor, and this is n by n minus 1 times R, and because n is 10, 10 by 10 minus 1 is 9, 10 by 9 times R, R is 1k, therefore 10 by 9 is nearly 1k, therefore I have put it as 1k. So, this is 10k, this is 1k, this is 1k also, and here I have a potentiometer which can vary from 0 to some value, usually it will be a 1k or 2k resistor here. Now, what will happen to the gain? When I put it to the minimum, I have now maintained the potentiometer to the minimum position already, and at the minimum position it becomes grounded, and therefore, it becomes a simple inverting amplifier. For an inverting amplifier, the gain should be minus 10 minus n. n is 10 here. Now I have taken the input from the voltage source here, which we have already seen, and what I have done is I have reduced the voltage by 10 times to the previous value. Previously it was 1 volt in the earlier experiment, now I have kept it as 100 millivolts, 0.1 volt or 100 millivolts. So that is what you will observe now, because I have connected the multimeter at the input terminal. If you look at the multimeter output now, you will say it shows 0.11, that means 0.1 volt or 110 volts, 110 millivolts. This is 0.11 volt or 110 millivolt approximately. So that is the input voltage. Now what I am going to do is I am going to take multimeter from the input and connect it to the output. See what happens. So now I have taken the multimeter and connected at the pin number 6 with this circuit wired here. So what will be the output? Because the potentiometer is in the minimum position, so the gain now is 1.01 is what you measure at the output voltage of the multimeter. 1.01 divided by 0.1, which is the input, gives me 10. So the gain is 10 right now. Now if I vary the potentiometer, I must vary the gain to minus 10. That means the output voltage should become minus 1 volt. From plus 1 volt it should go to minus 1 volt as I vary the potentiometer. That is exactly what I am going to do now. So you please keep observing the multimeter as I change the potentiometer. Now it is plus 1. As I change the potentiometer, the output voltage keep decreasing, 0.7, 0.6, 0.5, it keeps on decreasing still, and it comes to nearly 0, and then you can see that it has come to minus 2, minus 3, minus 4. I keep moving in the same direction of the potentiometer, minus 8, and finally when I come to the complete one, it becomes minus 1.01. Minus 1.01 divided by the input voltage, which is 0.1, gives me the gain, and therefore the gain is minus 10. So you can see all that I have done is vary the potentiometer from the minimum value to a maximum value, and the gain goes from minus 10 to plus 10 as I vary this. So it is a very simple configuration with only 4 resistors, 3 of them are fixed resistors and 1 is a variable resistor, and by changing the value of the potentiometer I am able to vary the gain of the amplifier by plus 10 to minus 10. I have used here n to be 10. If we want to change the gain to some other number, you can very easily do. For example, I can put here 50 kilo ohms, then I can have also this nearly 1k. There is no need to vary this, and then you would find by changing the potentiometer I will be able to vary the gain of the amplifier by from plus 50 to minus 50 continuously using the potentiometer. So you can put different resistors, and it is very simple. There is no complicated things involved here. It is a very understandable and reasonably very straightforward, and as soon as you wire the circuit you will be able to get the output voltage. So that provides a lot of confidence and for us to build different type of amplifier. The variable amplifiers are always very useful because we do not know what is the signal level. If the signal level is varying from very low voltages to very high voltages, then you must also be able to vary the gain correspondingly. When it is very low value of voltage input, then you should increase the gain, and when the voltage becomes larger at the input you should reduce the gain. So in several applications you would find the variable gain amplifier will be very useful, and you can make use of this configuration for achieving such variable gain amplifier. Now we have seen the adjustable and reversible gain amplifier. The demonstration also we have seen, the theory also we discussed. Next application circuit I want to show you is a very small variation of the same circuit, which is called a phase shifter. You find there are several applications where you would like to vary the phase of the output with reference to input without changing the amplitude, that means without changing the gain. So it is possible to do that using a single op amp in a very simple straightforward manner. So, you can see the circuit which I have shown on the screen. You have got the two resistors R and R prime, both are equal, R prime and R prime, and I have in the other circuit I have an R and a C. R is a variable resistor and C is the capacitor that is connected at the inverting non-inverting input. So, when I have a configuration like this and apply a sine wave input at different frequencies or any finite frequency, then you would find the output phase can be varied with reference to the input phase by changing the value of the R, having the gain 1, because R prime and R prime decide the gain, because they are equal the gain is only 1. So, the gain is 1 for this configuration, and but what is the advantage? The advantage is the phase can be changed from a value 0 to a value 180 degrees, 0 to minus 180 degrees you can change. Now, when I have the input frequency much lower than the cutoff frequency f, very low compared to fc, the capacitor appears to be open. We have already seen that. In that case, the total gain is due to both inverting and non-inverting, and therefore AV is equal to 1. This means that the output signal is having the same phase or 0 phase with reference to the input, and the gain is 1. When the input frequency is much greater than the cutoff, f very large compared to fc, the capacitor appears shorted, and in this case the non-inverting channel has a voltage gain of 0. The overall gain therefore is equal to the gain of the inverting channel, which is minus 1, and that means the minus shows that there is a phase of 180 degrees. So, what we have now is the same circuit with a potentiometer here, and we can shift the potentiometer from this end to that end, thereby I will be varying the phase of the amplifier from 0 to 180 degrees. The cutoff frequency for this is decided by the two resistor RC combination that I have here, and I have used here 1K and 0.022 microfarad. So, Fc is 1 by 2 pi RC. This is the well known formula that you know, and the phase angle is given by minus 2 arc tan f by fc. So, f by fc, f is the applied frequency, fc is a cutoff frequency obtained from this formula 1 by 2 pi rc. So, by using this for values that I have shown in the circuit, 1 by 2 pi rc, 2 pi r is 1 kilo ohm, c is 0.22 microfarad, and if you do that you get a control frequency of 7.23 kilohertz. So, when I have about 1 kilohertz, the phase shift will be 1 kilohertz by 7.23 kilohertz, that is minus 15.7 degrees. If I have the 10 kilo ohm increase to the 10 kilo ohm, then the corresponding phase shift can be calculated, because the cutoff frequency will now vary to 723 kilohertz, and therefore 1 kilohertz by 723 will become 180 degree, and when I change to 100 kilohertz, then it becomes 72.3 kilohertz, and the phase angle is 172. So, by changing the potentiometer, the RC value, R value, and you would find the phase angle can be varied by a whole range from almost 0 to 180 degrees. I will just show you the demonstration of this phase shifting amplifier. Now, you observe the circuit. I have a 1K here and I have a 1K here, R prime as I shown in the picture, and this is a potentiometer, and I have a capacitor which is about 0.22 microfarad. So, the input here is from a function generator with a sine wave oscillator output. So, you can see here the function generator to the left of the screen. So, you can see the function generator. I have chosen some 1 kilohertz as the frequency, 1.14 kilohertz, and the output is connected at the input of the amplifier here, and the output of the amplifier is monitored using an oscilloscope. The two traces that you see here, the two traces are basically the input and the output both together. So, you can see they are actually in phase. When the input is going down, the output also is going down, they are in phase. But when I change the potentiometer, you would find the one of the trace, the output trace will show a shift that corresponds to the phase shifting that I am talking about. For the same RC network, if you change the value of R and C, you will get different phases. Therefore, you would find the shift in the frequency, shift in the phase as seen by the shift in the trace that you see on the oscilloscope. Now, I want you to continue to observe the oscilloscope while I change the potentiometer, and you would find the trace slowly moving away. Right now, we can see that the trace starts moving to the right, and then I can go almost up to the 180 degree phase shift corresponding. Then I come back now, the potentiometer, now it is in phase. Now, as I move that, you find it is shifted towards the right, and therefore, the phase can be continuously varied from 0 to 180 degrees. So, this is a phase shifting circuit, and all the different 5 different circuits that I have discussed are very simple to construct, and I have also shown a demonstration how they can be used in different applications. Thank you.